For our project, we plan to be looking at a gyroscope. More specifically, why it is so hard to knock over. To do this, we will be looking at the properties and principles of rotation, figure out why they're so hard to knock down. In addition, we also want to find out the minimum angular speed needed to keep it from falling out.
Now we're gonna switch over to Steve with the gyroscope information. Take it away, Steve.
Okay, so I'm Steve with the gyroscope information, and basically, so we needed a way to make sure that the initial speed after it's like been spun is like the same, the angular speed. And so the way we did it is we attached this weight to the end of the string. It's a 500 gram weight. And then what we did after that is we just kind of drop it, and then, you know, the string is the same length every time. This thing is the same weight every time, and then gravity doesn't change. So it gets us a pretty consistent, you know, like angular speed. And then basically, ready? Here, show the timer so that we know it's valid. You ready? We just start the timer when it drops, and then stop the timer when it's not attached anymore.
Not enough space.
And you get about 1 second. What's up, guys? It's your boy, Steve here. Anyway, so Josh is going to explain to us how the acceleration... Okay, I'll let him explain it.
Okay. So, what's up, everybody? We're here with the gyroscope and our maths from last time. So we're going to find the angular acceleration by letting this drop and letting it come to a complete stop. The amount of time that it takes to do that will allow us to find the angular acceleration.
Alright, so the next thing that we need to talk about is why gyroscopes fall down. And the reason is gravity, you know, obviously. So basically what happens is when you first put a gyroscope down, it's pretty much impossible to put it like orthogonal, nice, to the ground. And so it's always going to be at a little tilt, and then gravity kind of pushes that side down, and then it kind of like, that tilt, the angle that it makes with the ground gets bigger and bigger as it keeps going. And yeah, so basically, if you take this disc and you spin it, and then I'm going to blow on it, and then me blowing on it is going to represent the gravity acting on the little tilt thing. It's not going to tilt down directly in the direction that I'm doing it. It's going to tilt down, like, you know, over here, because there's like the whole vector addition thing. Anyway, I'm just going to do it. Alright, so there you go. That's what happened. And then I have this. And this shows us that basically, if this is the disc that's spinning, you have the force of gravity pulling it straight down, then you have the momentum of it going to the right. And then, so yeah, it's going that way. And then, because that's like, you know, you just combine them. And then this shows you why the faster a gyroscope is spinning, the harder it is to knock over, or at least the longer time it takes. Because if it's going slowly, can you see this fine?
Oh yeah.
Yeah, okay, so if it's going slowly, this vector will not be, you know, won't be that big. So this will, when you do the vector addition, this will take up more. You can see that that's steeper. So gravity affects this more than it would affect this if it were going quicker, and that momentum is larger, and so it would go, you know, less down. Anyway, thank you for coming to my TED Talk. That was it. That was the whole video.
Hello, my name is Juan, and we are here in my bedroom, and I will be going over the law of conservation of momentum. The law of conservation of momentum states that momentum will always stay the same. And so, if the radius goes down, velocity goes up in order to fit the law. You know what I mean? So like, the ideal gyroscope is one that has a small radius and a low mass. Yes. And so, because of this, it increases the speed at which the gyroscope goes, and so like it's less likely to fall. Thank you very much.
Alright, what is up, guys? I'm going to be finding the torque of our gyroscope as it is accelerating. So if we start with our force diagram right here, we have our force of gravity with our constant weight that we were using to accelerate it, and we have our sum of forces that we discovered with mass times acceleration. But because as it's accelerating, there's a constant change in the force of tension, it was small enough that we deemed it just a constant. So we discover the force of tension right there, and we take that, plug it into the force times radius to get the torque formula, and our final torque was 0.0107 Newton meters. Using that, we can find the rotational inertia using our alpha equals sigma torque over rotational inertia, plugging in our values. Our alpha value was 980 radians per second, and plugging it in, we get 0.00011 for our rotational inertia.
Alright, so basically, you have the time that it takes to come to a complete stop is 142 seconds, and the initial angular speed is 980 and the final is 0. So you can find the average angular speed to be 980 radians over 2, or 490 radians, or 78 revolutions per second. Then 78 revolutions per second times 142.6 seconds is 11,079.6 total revolutions. And then that times 6.28, or 2 pi, you get delta theta equals 69,580 radians. And then you plug that into our equation for delta theta to find the acceleration, because we have the angular speed, we have the initial angular speed, we have time, and we have delta theta. So our only variable is this one. So then you can solve for it, and it is negative 6.901 radians per second squared.
So guys, while we weren't able to find the minimum speed required to keep it upright like originally intended, we were able to find the reason that the gyroscope falls and the fact that its spinning keeps it upright. We hope you enjoyed the vlog, guys. See you next time.